Okay, so good afternoon, everyone. So we will do the last part, and the last part is about coming up with some more algorithms. So what we have done so far are the first order methods. And of course, in first order method, we have seen the most prominent one is gradient descent. And we have seen stochastic variant of gradient descent that is used for neural network trainings. So there are many variants there we have seen, all the most prominent variants we have seen. But then what you observe is that all were first order. By first order, we mean we were only using gradient information. Okay. And even in first order, we can do some variations. And we can also introduce second order, okay, methods for that it requires second order derivative. Okay, so we presume that second order derivative will have more interesting information, right, regarding the curvature and so on. So so let us look into those kind of method from a unified view of so-called steepest descent. Okay, so steepest descent is something I'm going to introduce now. And let us derive this method. So first of all, let us assume that we have a function f for which we want to find the minimum. Let us do a Taylor expansion of f of x. So Taylor expansion of f of x plus v. Okay, so let us say at x around v. This will be the first order Taylor expansion, right? So, and we say that the Taylor expansion is an Taylor, since it is an approximation, that's why we use this approximation term. So the Taylor expansion of this is fx plus grad fx transpose v. Okay. So here, by definition, this is called directional derivative. Okay. So this is called directional derivative of f in the direction of v. Okay. That's the definition itself. So you can take it as a definition. So it's like in the direction of x in this case. Okay, here we are talking about v. So let me put it v only. Okay, so v is a descent if gradient of fx transpose v again, okay, is less than 0. Okay, so that is how we define a direction to be descent when the gradient of x transpose v is less than 0. Why is that? Like, we are talking about descent, right? So the function value should decrease, right? So I am at fx, and then I am at x plus b, and I want to know whether x plus v is less than fx. Then I am decreasing, right? So my first iterate was x. After that, my second iterate was x plus v, and so on. And in the minimization algorithm, I have to produce this sequence and then such that I keep decreasing the function value. And if we look at this, then we immediately notice that if this guy is less than 0, then indeed fx plus v is less than, fx plus this second term is less than fx, right? So if this is negative, then fx minus negative will be less than fx itself. Okay, so this will be less than fx. And this is what we want. F of x plus v is less than fx. And this, when this happens when this is negative, right? So from here we derive that. So what we see from here is that it's about producing a vector v such that gradient of fx we can compute at x, the current point x. So any vector that we want to produce, if that vector is such that the gradient of fx transpose that vector is negative, then that vector v, which is the direction, okay, that vector v is the direction to follow. I'm going to, okay, another matter that how much to decrease and so on. But in general, this is what we are seeing. Okay, in general, this is what we see, that choice of v should be such that the dot product with grad f must be negative. Okay, that's what we have. Here we see that grad f transpose x v is linear in v. Obviously, this is a linear function of v, hence can be made as negative as possible. Okay, so that's the property of of a linear function, right? So linear function is like the form alpha x is alpha f of v, right? So if I know that this guy is negative, then I can make it as negative as possible by the choice of more and more higher alpha. Okay, so if f of x is less than 0, then this implies for some x, right? This implies f of alpha x, which is alpha times f of x, tends to minus infinity as alpha tends to infinity, right? So this is because of the linearity. Okay, so this is because since f is linear. So this is the thing with linear functions, right? If I have a linear function and if I know that at one value it's negative, then I know that the function is going to be unbounded below. Okay, because that will like keep going to infinity. Remember that constant function is not a linear function. Okay, some people get confused with saying that constant function is linear function. No, constant function is not a linear function because it does not satisfy f of alpha x is alpha x. For example, for x equals to 0. So for example, it should be 0. Okay, because f of 0 is f of 0 times 0 is 0 times f of 0 and so on. Okay, so this will be 0. So linear function necessarily have to be 0 at 0. Okay, but constant does not satisfy this. So constant is not linear function. Okay, just to be sure. Okay, so in this case, obviously there is no hope. I mean, even if c is negative, okay, we cannot make it unbounded. Okay, but we are talking about linear functions. So linear functions here can get, if someone gives you a negative value, you know that the function is going to be unbounded for sure, right? Okay, so this is what we have now. So the problem here in this, the problem, what is the problem, right? What will happen if that is the case? It can be made as negative as possible. Is that I can I can choose a v that falsely leading me into unusual descent. Let me say unusual descent, right? What is happening when we are minimizing a function, right? So let us say I'm minimizing a function like this, right? So let us say my x is here, right? And so that's my some iterate. Let us say first x is x. And then how do we proceed in gradient descent? We take a gradient, right? So this points in the direction of increase. So grad fx. So we go in the negative, so to decrease. Okay, let us say we are doing the minimization problem. So we go to the negative fx direction, right? And that is in the Euclidean norm. Okay, all this will be covered in the steepest descent. So gradient descent will be a special case of steepest descent. But let me focus on a part here. Descent direction according to the gradient descent is minus grad f. That we know, right? So but the thing is, I can with this local information, I can be overexcited and say that let me choose v as far as possible because locally it's decreasing, but there is no guarantee that it is decreasing after some point, right? After that it is increasing here. Okay, so the point is that you have to have some restriction on how much what would be the length of your decreasing. Okay, so this is, let us say this is my v, so I cannot choose v to be here. Okay, then because then I may be increasing the value, or let us say v somewhere I choose here, then I this. So it tells me that I need to have some restriction on the length of v, although it may be a descent, but in general I should not choose a v so big that I overshoot. I mean, it's also true for convex function. Convex function is like this. So obviously I should not choose v so large that I move here and then x plus v is here, and then I actually increase the value based on just the local information. Okay, so by descent we mean locally for a small enough v I'm going to decrease, right? But one may get overexcited and say, okay, since it's decrease, let me decrease as far as possible. But that will not be a decrease because your decrease conclusion was based on the fact that you are locally in a small neighborhood, you are decreasing. That's what. gradient tells you. Okay, so that's why we need to limit the size of descent v. Okay, so we need to normalize v in some sense. Okay, some kind of normalization is needed. So this is the normalization I do. Okay, so rather than, so if I look here, I will create some kind of a norm ball here, and then I'm looking so that it's normalized here. So these are like unit directions to decrease, and I will be restricted within this this unit norm ball. A norm could be many types. Okay, we will see that for 2 norm we arrive at the gradient descent actually. So different type of norm give us a different view of the function, or in other words, more precisely, it gives us a approximation of the function locally. Okay, so it gives us approximation of the function locally. So, but then as I said, we have to bound it with some norm ball. Okay, that's why we do we are looking at descent direction, but within some norm. So this is a sphere. Okay, so this is a sphere of unit radius. Okay, and we are not saying anything about the norm for the moment. You have a different choice of the norm, and that's what we will see, that different choices of norm give us different variety of methods to choose from. Okay, so that tells us. So that is the reason why we are studying steepest descent, because we are creating a general theory of how we can descend, and what is the local approximation that we are looking at the function value, right? So these norms are like the local approximation of your function. Okay, you change the norm and then you are approximating functions in a different way. You're creating preferences basically. Okay, we will see. We will come back to this later. So remember that there can be multiple ways to descend. Okay, that's what we know also, right? So there is not necessarily a unique descent direction. Okay, so if this is a descent direction, then maybe this is also a descent. This is also descent. Of course, which is the steepest is what is like we may want to know. Okay, or it may happen that due to symmetry, you may descend in 2 different directions in the same amount. So both can be a steepest. Okay, even the steepest may not be unique, right? A function has a nice symmetry. Okay, so if a function has a nice symmetry, then you may want to descend in either way, right? So if I'm here somewhere, then if I'm descending, then I could have gone this way, or I could have gone this way, and both way I'm arriving at the same value. Okay, so I could have had 2 steepest descent direction. Okay, so that's why we say A. We will be saying A steepest descent also. It's fair to say A, okay, because there could be multiple. So okay, so there could be multiple minimizer of this guy. So now so this is what we are looking for. We want to descend, but in a normalized way. So so we can also define it to be like this without loss of generality, because, well, looking for vector with exactly 1 norm or looking for vector with less than equal to is the same thing, because this is a superset. This is a superset of this guy. Okay, so it's also enough. Actually, it's also enough actually to look into this. Okay, we are also including even less than. So if it happens that there is a smaller value of v for which I get a descent, why not even take that? Okay, so the steepest descent direction is about look in the direction of the unit ball that extends farthest in the direction of minus grad fx. Okay, so geometrically what this means is that I have to look into the direction that extends farthest in the direction of minus grad fx. Okay, so unnormalized steepest descent. Okay, so what does this mean? So this means that I can write unnormalized. So unnormalized was, yeah. So okay, so I'm introducing the notation again. So this is the unnormalized variant. This would be same thing as saying what is the maximum amount of stretch that I can do, and then the direction in which I can go. Okay, so the maximum amount of stretch I can do is this and times the direction which is already normalized. Okay. So the unnormalized, I can write this in terms of the normalized. Okay, and this is the dual norm of this. Okay, so whatever norm you choose here, the dual of that will be used here. So if it is 2 norm, then it will be 2 norm here because dual of 2 is 2. Okay, so I can write the unnormalized by using the normalized. Okay, so with that, I'm not going to explicitly prove this, so you can verify this, that that this quantity grad f transpose del the unnormalized one will be equal to the dual norm squared. Okay, so this is left as an exercise. For the moment, you just take it as a fact. Okay. So here, obviously, this is the dual norm of this, and this norms show up in where I am taking the supremum of these guys. Okay. Okay, so we will see this with an example so that it will be more clear to you. But what is the steepest descent algorithm now? So steepest descent algorithm says, well, we have to compute the steepest descent direction. Okay, so let us say that is del x as d, and then you choose a t via the backtracking. Okay, so via backtracking or exact line search, I have not done this, but for the moment you can assume that there is some line searching method that tells you how far you want to go. Okay, so once again, like my function is like this, and then I am here, and then the direction chosen for me is del x sd. Okay, so this is the direction I given to me, but then how far, I mean this direction. Okay, so how far I want to go will be decided by the step length. So maybe I will stop here. So those things will be taken care of in the exact line search and backtrack line search. I'm not going to do this, but let us assume that there is some algorithm that tells me how to find this direction. Okay, the normalized steepest the normalized direction is to find out in a fair way what is the correct descent direction. Okay, and so locally, what is the good descent direction? And the step length is to tell you how far you want to go. So normalized is telling me I want to do a approximation within this unit norm, and then I want to find the best descent direction out of this. Okay, so best descent direction within the, it's like as I said, right? So there are two things going on here. First is like how far I want to go, and then second is like how do I make the choice of descent? As I said, descent direction can be multiple, right? So there can be multiple descent direction. I can also descent like this. I can also descent if I go in this direction. I can also descent if I go in this direction. So to make that choice in a good way, I have to make sure that they are all in a unit norm such that this direction, and this direction can be compared. Okay, that's one thing. Okay, and then the second thing is like once I have decided on that, because how do you compare things, right? When you will compare things when they are not biased, right? So you can compare between different things when no one has a bias. So by taking these norms, you are removing any bias they might have, so that they are all allowed to have a unit norm movement from the current direction, and out of that you are picking the best descent. Okay, so that is helping you in the choice of the direction. Okay, and then the step length is telling you how far you should go so that you will keep descending. Okay, there are algorithms to do that. I'm not going into that, but let us assume that there are algorithms to make a choice. But the first is like what is the good direction? Okay, and then once you are in an unfair way, so that all the vectors are given the same norm value, and then the next step is to what is the step length that is computed by the backtracking. Okay, so this is the steepest descent direction. So then the steepest descent direction, it's about what is the good direction, because there are many directions to go down. What is the good one, depending on the algorithm at hand, right? Okay, so let us look into some examples so that you will get more clarity. So let us first get into a familiar Euclidean norm. in Euclidean norm, we are looking to do descent with norm of v equal to 1. Now, here is when you choose a norm, you are creating a preference for yourself. Okay, it's like a let us say you are going for a trekking. Okay, let us say you are going for trekking in Himalayas, and you put some kind of googles. Okay, and these googles create an illusion for you, a approximation for you. Okay, because what I'm seeing when I'm going the trekking, then that is my view of the space, right? So my view of the space then maybe is isometric in the sense like I see same things in a uniform way. Okay, so that will be the spherical view of your function, right? So if I'm doing here, then I'm here. If I'm doing a 2 norm, then it is a perfect sphere. So for me, it's like any direction is for me it's a uniform direction. So things that are I mean the things that I see them to be equally distant, they have, I mean, they are also equally far. Okay, so that's what it means in the 2 norm case, because it's a sphere. So it's like a no specific preference given. Okay, in at this location. So that's what this means. So and that is what we believe. So we believe that in our the space that we live in this world, it's more like an Euclidean, we believe. Okay, but there may be like if you go into like the more higher end physics, then you will see that there is a distortion of space and time, and that is happening because there is some certain preference in certain directions. And these are the things we see sometimes. Let us say the sun looks bigger when it comes out in the morning and so on. Okay, so there is some kind of distortion happening there. Okay, so that's why things look bigger and so on. So there is some preference being created there, and those are happening. So you can think of norm like that. The norms are like that. Norms are like creating distortions in the space. But if I take an Euclidean, then it's like a uniform in all directions. Okay. Okay, so let us see if I choose this norm, what do I get, right? So now, if I choose a 2 norm, then what is the arg minimum of this? So what is the minimum of this? Well, if I see this function, grad fx transpose, right? So grad fx transpose, and what would be the choice of v that will maximize, that will minimize this, right? So I know that this is a dot product, right? So grad fx transpose v is a dot product, right? So it's a dot product of grad fx and v, okay, or v grad fx, okay, either way, the way you define dot product. Okay, so this is a dot product. So dot product, when is the dot product maximized? When this guy is in the direction of this, but we are talking about minimize, right? So I will take the opposite of that, right? So this and this guy will so v vector and u vector, right? So the dot product, so we have to take it in the opposite direction of this, so that I get the minimum value for the dot product, right? So that's why I choose a direction v which is in the negative, but then I normalize, right? Because the norm should be 1. So norm should be 1. So I know that I have to go anti-parallel to grad fx, but then since steepest descent demands me that all should be within the norm, okay? Although the norm itself can create distortion, but for the moment we are not in that case. We are in the Euclidean norm, so there is no distortion at all, and we know that the dot product is maximized when you do grad fx and minimized when we do minus grad fx, and then we normalized. So we normalize this, and this is the place where this is going to get this is the steepest descent in this norm. Okay, I mean the steepest descent direction for the moment. Okay, our choice right now is for the direction. Okay, and then so this is just we are talking about normalized when we are making a choice of the direction, right? And then if I have to now compute the actual descent vector, then I know this this was the result that we discussed before. Okay, so this is how this is defined. Okay, this was left as an exercise. So this will be the dual norm of grad fx, and then delta of the normalized that we have. So if we, so the dual of this 2 is 2 itself. So that's why I have grad fx2, and then del x nsd is taken from here. So if you multiply this out, you will see that this is negative grad fx, and this is the gradient descent that we know. Gradient descent. So a gradient descent is nothing but steepest descent in the 2 norm. Okay, so gradient descent. So this is left with an exercise. You can see this, I think, proof in Boyd also. Okay, so this is how we derive the gradient descent. Gradient descent is the steepest descent in the 2 norm. Okay, so that's gradient descent, and so the blue direction is the preferred as it aligns with this, and then among all the vectors of same length, the one that aligns with this will give the maximum possible distance. So that's what I said in words before. Now let us look into a quadratic norm. Okay, so now we are trying to derive some new algorithms in the steepest descent framework. And how will you do that? By just changing the norm. So steepest descent is a family, creates a family of algorithms. So let us see how, if we change the norm to p norm, what will happen? Okay, so let us see that. So the normalized steepest descent direction will be the minimum of this quantity for all v whose p norm is 1. Okay, so p here is assumed to be symmetric and positive definite because that is when it will be a norm. Okay, this is a matrix norm now because p is a matrix, and matrix norms are a norm when the matrix itself is a symmetric and positive definite. Okay, otherwise this norm may not be, because the norm is defined to be square root of v transpose px, right? So then yeah, that's correct. Yeah, so v. Okay, so to make a norm positive, because norm has to be greater than or equal to 0, right? So this will be greater than or equal to 0 only when is guaranteed to be, because when p is positive definite. Okay, so this is how we define. That's what I said, square root of z transpose pz, and I can write like this also, because this guy I can write this as z transpose p half. I can do a p half because p is positive definite. So square root of a matrix exists, and then we do this. We do this, right? So half z transpose p half z norm, right? This is u transpose. So this is u transpose is norm of u, right? And over on the power we have half, so that's why it's just yeah, we have this quantity, right? So now let us see what this quantity is. So I define v star to be arg max of z transpose v. Okay, under this condition that norm of v is 1. So just let us focus here. Z transpose v, we want to maximize this, right? So it will be this is Z transpose v, and okay, and places where v is this is the same thing. Okay, yeah, okay. So p norm. So this is what I have used. Okay, so vp will be p half of v. So p half of v. Okay, so that's what is assumed from here. Star. From star, I can go from here to here. Now x star, let us define x star to be argmax of z transpose p minus half x. Okay, and norm of x equals to 1, and yeah, yes. So v star, so v star will be p minus half of x star. Okay, I think we are defining. I think we are defining p half v. Yeah, okay, I see. So I think I have defined p half of v to be x. Okay, so define p half of v to be x. So there you get 2 norm of x equals to 1, just follows from here. And then, but then here you have v, so you want to change back to x. So v will be p minus half of x. So that's why you get p minus half of x. Okay, so and then you can say that you are looking for x star now. Okay, and v star from here will be p minus half of x star, obviously. Okay, and yeah, so and what is x star, right? So x star, okay, so why, you see that the tricks that we are doing is, although this is a matrix norm, we are getting into a familiar territory of the 2 norms. Okay, and in 2 norm we know what is the maximum, what is the solution for this, right? So that is the trick we are using. Okay, from p norm you move to 2 norm, and then this we know, right? So this will be again by the previous logic, the choice of x will be, so this is the dot product of this, right? So Z transpose this with this. So the choice of x for which this will be maximized will be the same guy, right? And then since it is the norm 1, so the choice of x I will take here will be a transpose of this guy, right? So transpose of this guy will be p minus half and then z. Okay, okay, so this is like u v, when is this maximized? Okay, let us say u is fixed, then this is when v is in the direction of u, the dot product is maximized, that's when. Okay, then the cost 0 is 1, that's the maximum you will get, right? So that's why we will choose this. Okay, so v is like, so that's why we will choose x to be this. Okay, so that it's along the same, but then the restriction on x is that it must be norm 1. So I have to divide by the norm of this guy. So p minus half z. Okay, so that's what we did here. So that's the proof of this. And yeah, so we go back to v star, because v star is the one that we needed actually in here. So v star will be this guy. Okay, and okay, so yeah, so maximum of Z transpose V. Yeah, so maximum of we also know that maximum of Z transpose V will be the dual norm. Okay, so that's how the dual norm is defined, right? So Z star is this, which is Z star, but then maximum of this we have seen before. This will be given by the V star that is known to us. So V star I substitute here, which is here. Okay, and this is the V star, and Z transpose is here, and V star is this guy. Okay, so that's what we have substituted. Yeah, so now let us see, can we find it now after all this? Okay, so so that's like arg mean of F transpose this and this. So this is the same thing as here, and this is okay. So arg mean we can change to arg max by taking a negative here. So you've done a negative here. So that's the mean to max change that happened, and now we take Z. Now we take Z to be minus grad fx on the left. Okay, so it's like I am maximizing this, right? So this is now this is the result I'm going to use, right? This was the separate result that we did in view of proving this. So now we started here and then we moved to this guy. Okay, so here we used some arbitrary Z, but what our intention is to work with grad fx, right? So this is our Z now. So this is our Z according to the calculations that we have done. So this is what we need here. If I substitute Z by minus grad fx, that's what I need. And for that case, then I can obtain this. Okay, so Z will be minus grad fx, and then delta x NSD will be, yeah, so I put Z to be minus grad fx divided by norm of p minus half grad fx. Okay, so this is the estimate I'm going to have. Okay, yeah. Right. So finally, what we can conclude is, so we know this always, right? So del SD, that's the actual descent in the algorithm that we need. It will be dual norm of grad fx star. So I mean the dual norm of grad fx, del x NSD that we found here, and yeah. So if I multiply, if I have this, okay. So where will I get this? Grad fx dual, right? We can get it. Yeah, let's see. Grad fx star we need. Grad fx star I can get from here. Yeah, so it, and then we have P inverse, right? Okay, and grad fx will be left out. And so something should get cancelled. So grad fx star I can get from here, and delta is there. Yeah. Yeah, in place of Z. So what we have to do now is the following: grad fx, I mean the norm star is Z, so not Z. Now in place of Z we have fx, grad fx transpose p minus half grad fx divided by norm of p minus half grad fx. Okay, and this times this. Okay, so yeah, so this calculations I believe is left up to you. So you have to multiply this part. So p minus half, some cancellations will happen, grad fx by norm of p minus half grad fx. Okay, so if you multiply these guys, okay, so this will be a squared, and then you will have something on the top, right? Yeah. So I believe what will come out is grad fx transpose this, and this is a transpose of that. Okay, and in the middle I have grad fx. Okay. So essentially this should simplify to this. Okay, so this should simplify to this. I will leave this for the moment because it might take time. Today is the last class. Or maybe I will put this in the Moodle. Okay, so that you get this. Okay, so this is what eventually I'm supposed to get. In the p-norm case, then in the p-norm, the descent direction that you're going to get is this. So this is the inverse of the matrix P itself. Okay, so that's something we note here now. Okay, this derivation is left, but you can check that this should be actually this. Some cancellation should happen. Okay. Okay. So we have seen some other variants. So previously we saw when we choose Euclidean norm, then we got exactly the gradient descent. Now the descent that we are getting is not exactly gradient descent. It's something else now. So it's not minus grad fx. It's now minus p inverse grad fx. Okay, so that's a different algorithm. Now what is happening in this intuitively is the following. If you are taking a norm like this, okay, if you're taking a norm like this, what does this indicate? right? So if I'm writing like this, what does this implicate, right? So, indicate, right? So if I say this, then according to the definition here, I have V transpose PV, okay, half is equal to 1. Okay, this is what it means, right? If I square it, then V transpose PV is equal to 1. What does this denote? Right? This denotes ellipse, right? We have seen before, right? And the ellipse major and minor axis and the curvature will depend on the eigenvalues of P. So that's how the norm is looking now. Okay, contrast this with the Euclidean. Right? In Euclidean, it was a perfect sphere. Now, by choosing a P norm, you are creating a unit ball like this. And in this, now you're talking about what is the good steepest descent direction. Okay. So this is a ellipsoid unit ball centered at x, and normalized steepest descent direction at x extends as far as possible in the direction of grad fx. So if you one possibility is that I go into the negative grad fx, okay, but the thing is it may not be the steepest in this. So if I go in the direction of minus grad fx, then I will go out of my ball. Okay, this Euclidean I mean ellipsoidal ball, right? So that is one possibility, right? So that's one possibility is like I go in the grad fx and then I go I can go as far as possible, obviously. But then my restriction is that I need to stay in the ellipsoid. So if I stay in the ellipsoid, you come up to here. Okay, and recall that if the norm is the 2, the best direction was this. So if the norm were a Euclidean norm, then the best direction we know already would have been minus grad fx. Now, since the norm is stretched more in the direction other than minus grad fx, so we know that this norm is stretched more in this direction, actually in this eigenvector direction. So this will correspond to the largest eigenvector. So this is the largest eigenvector direction where actually it is stretching more. Okay, so it is better to go actually in that direction of the most stretch. But what will happen is that you are indeed increasing the angle. Okay, you are increasing the angle. If you are, look, we have to compare with the Euclidean. Okay, so imagine if you were in the Euclidean, then you would have been happy with going in the minus grad fx direction. Now you imagine that you are in the ellipsoidal, then although from the Euclidean point of view you can descend, but then in the new norm, you are allowed to stress a lot more. And since this is also descent, maybe you will decrease a lot more. You see what is going on here? What is going on here is that the norms that you are creating is creating a stretch, a preference in your space, and this preference is now no longer along minus grad fx. Okay, it's around the direction where the stretch is more, because then the descent will be more, although there will be a trade-off with the angle corresponding to grad fx and so on. So here there is a trade-off in making less angle or going with the more stretch. Okay, because making a less angle with grad fx, because it is a uniform, it is a universal fact that grad fx for any function, grad fx is the direction of the increase, steepest increase, and hence minus grad fx. Okay, so we believe would be the direction of the steepest decrease. But the fact that we have created a preference by choosing a different norm, now the grad fx may not be the steepest descent. Now it may be something that goes in the other direction, and that hint comes from when we write down the dot product, right? So this is the dot product. The dot product can be written like this. So it depends on, dot product depends on norm of the gradient, and then the norm of the direction that I'm going to go, and then the cos of the angle between them. Okay, so what is now variable in your case, the choices that you have are out of this, because this is fixed at the current point x. So there is nothing you can do here. So now you have a trade-off between this and this, which one you want to play with. So if I choose a theta small, okay, so that would mean that I'm going in minus grad f x direction. Okay, so that's one thing. But another thing is like I allow the theta to be larger, but then I am going in a slightly different direction where del x NSD is bigger. Okay, so here this is bigger than this delta x and SD. Okay, so there are like multiple choices of this, but the one for which I'm getting the minimum steepest descent is this. Okay, so it's now no longer about just the angle, it's about also the preference that I have along which I'm allowed to go in stretch more. Okay, okay, all this will look all this may look a bit puzzling to you right now, like what I'm doing, right? On the one hand, I'm saying I have to decrease, and then I'm saying, then I'm creating unusual stretching of my space, and then I'm saying no, now you go into some other stretch direction. But then you will say, if that is what you already wanted to do, then why didn't you just stretch in this direction itself? If the stretching was the main thing for you, then why didn't you go and do the stretching in the original minus grad f x direction? Because minus grad f x was the one that you told me is the steepest decrease of the function, right? So all these things look puzzling, right? Like, why are we doing things in a round and round way, right? So there is a more deeper thing involved here. And the deeper thing that is involved here is about the local approximation of your function. Okay, so local approximation of the function, which is grad f x, that tells me that locally for a small neighborhood, I will benefit by going in minus grad f x direction. In other words, I will decrease the function value if I go in minus grad f x direction. Okay, but then if I'm using a different norm, then I'm creating unusual stretching. Okay, that's fine. I created unusual stretching, and why would I do that? Right? I would do that only if I have a better approximation of the local approximation of the function. If I don't have any better local approximation of the function, why the hell I will do unusual stretching of the space and so on? You see my point? Now the question is, how do I how the norms are related to the local function approximation? Right? Now that's the main question now, right? So if the only thing that I know is the grad of fx, then Euclidean norm is the only way I would say for me to proceed, because I have no other information. Okay, but remember, you also have information you can get if you want. You can get a double derivative of fx, and you can get a second order information. Now that's the trick. Now if you do a second order approximation, what you get is grad fx. Grad fx is the Hessian, right? Okay, then it's interesting now. So grad fx, grad square fx can be found, and that is telling me that it's a Hessian. So it's like, if I choose the matrix P in my P norm to be this, okay, to be the Hessian itself, then it's like I am creating a local curvature information. Okay, local curvature information of my function, and that is better than doing a spherical approximation. Okay, now you see what I'm trying to say. So let us say I have a quadratic function, right? So quadratic function, let us say P is symmetric and positive definite. In other words, the Hessian is like this. It's for a Hessian for a convex function. But let us see. I am here, right? So if I am here, then if I choose a Euclidean norm, then it will look like this, right? But if I choose a Hessian norm, then it will make approximation like this. Okay, and that is important because now it has created a local approximation which is matching with the curvature, because this is a quadratic function. So locally a quadratic approximation is better, right? So then it created a preference for me in this direction. So now it is telling me that you are allowed to go much more than what you could have gone in the Euclidean direction, if you have chosen the Euclidean norm. So choice of a Hessian as a P is giving me a better local approximation of the function, okay, and that is allowing me to decrease more that is allowing me to decrease more rather than having this isotropic equal view in all direction. Okay, so norms are very deeply related to the curvature information of your function. Okay, so that's what we are getting into now. So now you see why I choose a different norm, because different norm leads me to a different approximation of my function, and an approximation of function does not have to be spherical. Okay, if it's a quadratic, then it has to be some ellipsoidal approximation that will be a better approximation, because it's approximating a longer up to longer stretch. It's approximating it in a good way. Okay, so that's why we have this. Okay, so let us. Okay, so and we can also, as a practice, we can. So we have seen L2 norm, we have seen P norm, and now we want to play with one more norm just to see what are the things that we will get. So just by changing the different norms in the steepest descent, you keep getting different algorithms. Okay, so let us see what will happen if I choose L1 norm. Okay, so what was the L1 norm? L1 norm was the max of the individual the vector, right? So mod of x1. Okay, it's the sum of the xi's. Okay, I equal 1 to n. N is the length of the vector. Okay, so that's the L1 norm, right? Okay, so consider the steepest descent for L1 norm. So now I change the norm to 1 norm. Okay, so now what will happen is that now your balls look like this. So you want to create, you believe that your function can be better approximated in this norm locally, obviously. Okay, so in other words, you are creating certain preferences in certain direction. Okay, now what will be the dual? Because we need the dual also, right? So dual will be the infinity. Okay, so dual of this is infinity. So the one way to check is 1 by P plus 1 by Q is 1, right? So so if it is if P is 1, okay, then for the dual, what is left for you is that infinity. Okay, and similarly, if P was half, then the option that you are left for the dual is half only. Okay, I mean not half, but the P is 2, then the option that is left for Q is 2 also. That's why the dual of 2 is 2, dual of 1 is infinity, dual of infinity is 1. Okay, so basically they have to satisfy this. Okay, so in this case, the dual of 1 will be the infinity. Okay, these are like well-established things. So infinity norm we know is the maximum of the components of a vector, absolute values of that. Okay, now these are, Z is used as a just shorthand notation, but then what we are working with is Z is grad fx, right? So now choosing grad fx, then I be the index, such that, so what we need is the maximum of this, the component, right? So grad fx is a vector. So now the infinity norm is the index I for which grad fx, the component, is maximized, right? So we can say that that component is I. So let us say infinity norm is del fx by del xi. So the ith component of the grad fx vector is the maximum value, and that will define the norm. Okay, infinity norm. Okay, so what is happening here, right? What is happening here let us see. Remember, these are maximums over the components of a vector, right? These are maximum over component of vector, right? And what we know, so let us say z vector, right? Z vector, when we see z vector, we see this as z1, z2, and zn, right? As a component like this, and we can write like this: z1 in the basis of typical basis, right? And z2 and 0, 1, 0, and so on, right? And then zn and then 0, 0, n, right? So what is happening here is like when I do a max, it's like I'm picking which axis has the largest component, largest stretch. So now I'm moving into the axis, right? So let us say some is I here. So let us say this is I and some zeros are here. So it's like ith axis. If the ith axis has the most stretch, that will define the norm. Okay, that will define the norm for me. Okay, if the ith axis has the most stretch. Okay, so now it's about. So in the previous case, we have seen we had ellipse, and in the ellipse, the stretch was defined by the eigenvalues of eigenvector, eigenvector. And in this, so this is for the p norms, an eigenvector of p, right? And in this case, the maximum stretch is defined by the largest component, or in which axis you have the largest component, and that is the direction you are supposed to go. Okay. So in steepest descent for L1 norm, okay, so all this is we can put directly all those data here. So this is what we have. Okay, so the normalized direction is the axis where I am going the larger, and that is the axis is the ith axis. So that's why this is 1, 0, and then I, and then 0, 0, 0, right? So that's the ith axis. And then what is the value? Actual value is given by this, right? So this is what I have. Okay, and I have to go in the, because I have to minimize. So maybe like I will go in the negative direction. Okay, so negative of that. Take the positive value, go to positive, but I have to descend, so I have to go to negative. So I take a negative value of that. Okay. So if your descent directions are like this, and this is easy, right? This is an easy thing to do. So you can also do stochastic gradient and so on. Okay, so you can extend this to stochastic cases. And even like the second order method, like we have seen, that can be extended to a stochastic case. Okay, I'm not going to that, but this is easy, right? Because you have, because in gradient descent, you anyway compute the grad fx. Okay, so what this says is that rather than going to minus grad fx in the Euclidean norm for the steepest descent, it's telling you that you only go in a component wise way. Okay, so it's saying that although your in the Euclidean framework, your descent to a direction was minus grad fx, but you prefer to move only along one of the component. Okay, so let us say this is the x-axis and this is the y-axis. So this is the x-axis and this is the y-axis. And what you prefer is that you want to go in del f by del x1. Okay, so this is the x1 is the x-axis. So there's and this direction was del f by del y. Okay, and since you found that this is the most highest value, and you have to go to the minus, so you did a minus of that. So this is how you do in L1 norm case, where you move, but you move only along the coordinate axis. So next time you may move this way, only along the coordinate. Next time you move this way. Next time you move this way. Okay, next time you move this way or this way. So it's only like this way. Okay, up or down, right or something like that. Okay, but you will never go diagonally or something like that, because you are only following the coordinate axis. Okay, so that's why it's called coordinate descent. Coordinate descent is a very popular algorithm. If you search coordinate descent in a Google, you will see so many hits. Okay, but as you can see, this is just a special case of steepest descent. Steepest descent with L1 norm is coordinate descent. Okay, so that's what we know from here. So I have shown you like three algorithm, the gradient descent we already knew anyway, but two new algorithms came out of this. Is one is like pnorm. Now p itself, people vary, okay, and you can get variety of things like L, BFGS, and so on. Like variety of things are there. You can get a approximate Hessian, the Hessian that gets updated after some time. So all kind of variants are there for second order as well. And then you have coordinate descent. You can make a stochastic variant of this, and so on. So analysis of the steepest descent can be found here. If you have time, you can go ahead and read this and see why it will ensure the descent. Okay, so I'm not going into the analysis now. Okay, so let us dig a little bit deeper into that P norm case where P is now Hessian. Okay, I already gave you an intuition of why Hessian will be important. Hessian will be important because Hessian norm will give me a local second order approximation of the function, and the preferences of the direction created there is much better. Okay, because I have a better approximation of the function. Quadratic is a better approximation than linear, right? Okay, so then with the choice of P to be like this, the Hessian, we can have a so-called Newton step. Okay, so Newton T. Okay, so Newton step descent can be like this. So if fx is convex, assuming that fx is convex, then we can show that it's a descent direction. Okay, because this is negative, right? And since fx is convex, this is positive definite, and there is a negative here. So this overall is greater than equal to 0, but then you have a negative of that. Okay, so if you are assuming it's strictly positive, strictly convex, then this will be greater than 0 strictly, because if f is convex, then the Hessian is greater than 0. Okay, strictly positive definite. And if it is strictly positive definite, then some vector u transpose the Hessian times u, due to the positive definiteness, this whole thing will be strictly greater than 0 because of the positive definiteness. And then you have my negative, so it will be strictly less than 0. And hence, this is the descent direction. Remember, descent direction was the direction for which grad fx transpose v, right? V was less than 0. So this is the v that we are looking for. Okay. Hence, Newton step is a descent direction. Okay, Newton step is a descent direction if the given function is a convex function. Okay, for convex function, just by taking P matrix as a Hessian is a guarantee for a descent. So Newton method minimizes the second order approximation of f, obviously. So Newton method, we can write a second order Taylor approximation, and this is convex and quadratic, that can be seen, and it is minimized for the choice of v that we have here. Okay, so yeah, so you can check this. Okay, so as I said before, okay, I have already given you an intuition behind that. Is the approximation that you're doing, the local approximations you have with the Newton method is, so this is the dotted curve. No, not dotted, but this f is your original function, which is convex, and then you did a second order approximation here. Okay, so you did a second order approximation, so it's nicely matching with the curvature. But if you had done like some other isotropic kind of thing, then your approximation is only good very small part, right? It's very good only in a small part. But here it's nicely matching for a large extent. It's matching because because the quadratic approximation is better, so it's capturing the curvature a lot more. Okay, so that's the okay. So if f happens to be quadratic, then obviously because the Hessian will capture the quadratic information exactly, so that will be the exact minimizer actually. Okay, if the function happens to be quadratic, you will get an exact minimizer because your approximation is no longer approximation, it's exact. Okay, but yeah. So the quadratic model will be very accurate if x is near x star. So that is true because, so that's why you will see the Newton method starts converging very fast when it is already near x star, because for any function like this, so if I am here, then I believe that the quadratic will be very accurate. Okay, and once I'm near the function, right? So let me do something like this. Okay, so here you can say that quadratic approximation will look like this. Okay, and here if I do quadratic approximation, it look like this. Here I do it like this, but the moment I'm close, it's exactly matching. Okay, so this is the approximation that I did. So when I'm near x star, because when I'm near S star, then the quadratic will overlap and then I will rapidly converge. Okay, so that's the idea. And so the Newton method will, so Newton method convergence usually you see like this and then it drops like this. Okay, so it's usually because at other places it may be far from quadratic, right? Because the function values are like very oscillating, right? So I'm doing quadratic approximation like this, like this, like this. Here it's bad, okay? But then moment I am arriving here, it will be very exact. So that's why initially the progress you will make is not so good, but once you are near, it's exactly quadratic and it drops suddenly. Okay, and there is a concept of so-called Newton decrement, and that is used for analysis actually. So I will like skip this part. Okay, let me skip this part. Newton, yeah. So Newton algorithm can be described like this, provided that you assume this parameter lambda square. Okay, that's coming from the Newton decrement. Okay, so the Newton step is like this, obviously, and then lambda square, this which is so-called Newton decrement that I just skipped now, that can be used as stopping criteria. Okay, so that can be because these gradient values and Hessian is known to you, so you can find these values. You need a linear solve here, the matrix inverse times vector, right? So all this you can do, that can be used as a stopping criteria, and moreover you can use some ad hoc line search or some step length, or you can use some line search and so on, and then you update like you do in the gradient descent. Okay, here it's plus because negative is already taken care of here. Okay, so this is the Newton method. Okay, so this is the Newton method, and the main thing in the Newton method is that now you need Hessian, which may not be easy to compute. Okay. So as I said before, in the Newton method, you need to solve systems like this. So remember del x Newton step is Hessian inverse minus of Hessian inverse the gradient, right? So minus of Hessian inverse the gradient. Okay, so you need to solve the linear system. Okay, so solve the linear system, and if it so happens that H is symmetric matrix, then there are existing algorithms, so-called Cholesky factorization, that can factorize this into LL transpose, and then you can solve this in two parts. So I am supposed to solve H del x and t is minus g, assuming that there is a numerical routine that gives me this, where LL transpose del x and t is minus g, where L is lower triangular and L transpose is upper triangular. That's the important part, and that is what will make this simpler. Okay. So what I can do is that I can take this as W. So then the first step is that I will solve LW is minus G. So this is a lower triangular. So this is a lower triangular matrix. So it is easy to solve with lower triangular matrix by a forward substitution. By forward substitution, I mean the lower triangular matrix looks like this. Okay. So first I solve for this x1. And here I have B. So first I solve for x1 because there is just one thing here, and then I have two values here, but then one with x1 is already known, so I can solve for x2, and then these two are known, so I can solve for x3 and so on. So that's called forward substitution because I go in this way. So this can be done. And now once I'm done with W, then I know this, right? So L transpose del X and T is W. Now W is known. Now from here I can find X. So solve for X, solve for delta X and T. And you can do this because this is now upper triangular. Okay, so this will use backward substitution. Okay, so backward substitution is like upper triangular matrices are like this, right? So in this case, you can first start solving for xn, and then once you know this, then you know xn, so you can find xn minus 1 and so on, and then you can arrive and finally you can solve for x1. So there is a way to solve for this. So this is the main part in the second order method to solve with the Hessian. Okay, that's like additional thing, and here you need to use some linear algebra for a linear system solve. Okay, and you can do this Cholesky factorization if you are given that H is positive definite. If H is positive definite, then such factorization exists. Okay, so this is how we will get this, and Newton decrement can be computed. So Newton decrement was G transpose H inverse G, and using the fact that this H can be decomposed like this, I can write it as L inverse G, which is W, and the norm of this. So I need one solve with L, and then I take a norm to get the norm square to get the Newton decrement. So there are costs involved. For example, if you do a Cholesky, then the cost will be O(n) cube. So it's a matrix algorithm, n by n matrix. So the factorization cost is n cube. And if H is sparse, then obviously iterative methods can be used, like Kralov subspace method and so on. Okay, and if H is sparse and large, you can also use some iterative method to solve linear systems of this form. Okay, so there are iterative methods to also solve. So you start with some initial guess and improve on the guess and so on. Those methods are called iterative because you keep improving on the X values. Just like gradient descent, you have to update X. Now to solve this within the gradient descent, you have a method to solve for the linear system now. Okay, so there are theory of iterative method. I'm not going into detail behind this. So there is precondition CG to make your iterates faster and so on. Okay, so and yeah, and then you can use preconditioners and so on to make the convergence fast. So I can skip this part. Okay. Okay. Now one can let us focus on this equality constraint problem. For instance, fx, and then subject to x equals to b, where f is twice continuously differentiable. Let the x star exist and p star be the optimal value, and recall that x star is in the domain of f. So this is the optimal point and this is the optimal value, right? So, and it is optimal if and only if there exists a mu star. So this is something we have done before. I mean, done before in the sense like this is just KKT, right? So these are KKT conditions, right? So you write down this is the KKT condition, and that's the necessary and sufficient condition, right, for the optimality, which are KKT conditions. So solving the equality constraint is equivalent to solving the KKT constraints. Okay, so that's what we see in this equality constraint problem. It's about solving the KKT conditions. Equality constraint quadratic convex and quadratic program. Okay, so let us see what is this. So here f is twice continuously differentiable, and A is rectangular, where a rank of A is P actually, because the P is less than n, and P is symmetric. Okay, and okay, yeah, here P is symmetric. Okay, P I think corresponds to, I think this was supposed to be written like this. Yeah, and this is the P we are referring to. So this is the quadratic problem, right? So the objective is quadratic. So this is the quadratic, and equality constraint quadratic problem is like this. And this problem forms the basis of the Newton method. Optimality conditions in this case will look like this. So since this is a quadratic of the form x transpose px, if I take a derivative, I will get this term now. Okay, so p star px in my KKT conditions. So in this case, if you know that this is of the form x transpose px, then this is the way you will go ahead to solve. Basically, you just write KKT condition, and after that you see that it can be assembled as a linear system. OK, so in this case, yeah. So the things to remember is like A is rank P, right? So these are there, like the variables are there and unknowns are there and so on. OK, one can find out. So this method is almost the same as Newton method without a constraint. And so what is the Newton method for this, right? So the initial point must be feasible. Let us say we start with some initial point and make sure that that the direction that we are taking is a feasible direction, because remember that we are minimizing over x, right? But then it has to be feasible, right? So yeah, so it has to be feasible. So it has to be B, isn't it? AX must be B, right? No, that's fine. So AX must be equal to 0 so that x plus delta x nt will be, okay, will be actually B. Okay, and that will happen because this implies AX plus A delta x nt is B, so this must be 0. Okay, so the descent direction that you're choosing should be such that A times this must be 0. So if we want to derive a Newton step for the equality constraint problem, then replace the objective. So we can replace the objective like this. OK, and so we are assuming that we have V is the descent direction, and similarly, so X will get modified by X plus B, and here also in the equality constraint. And it's a quadratic optimization problem with equality constraint. OK, so the Newton method is a method on applied to this. OK, so Newton method can be seen as a method that is applied to this. In other words, it does a quadratic approximation of the function. OK, and then since we also have equality constraint, we also have update for the x here. And if we now try to solve this, remember our original problem to solve minimize f of x, that may not be necessarily quadratic. OK, subject to ax equals to b. That's our original problem. Now we are saying that the Newton method is a method that does the quadratic approximation of the function and also satisfies the equality constraint. OK, so if you do that and then you apply the KKT condition, then you get this. And then if you write this thing in the linear system, then this is what you get. In other words, your original function could be anything, but then you can solve it via Newton method and it will look like this. OK, so given a problem, minimize f of x subject to the equality constraint. We are talking about equality constraint also. OK, so ax equals to b. How will you solve this via Newton method? You solve this using Newton. Basically, you approximate it quadratic. That's what there is a gist of Newton method is that you do local quadratic information and then you approximation and then you write the KKT conditions, and that's what it boils down to. OK, so yeah, so this is the Newton method. When someone gives you a problem like this, then this is the way to solve. OK, by a second order method. OK, so this is like a second order method now, right? Because you need a Hessian information, right? If you had used a gradient descent, then you don't need, right? But now you are you're needing second. But one more thing is like, yeah, there is a equality constraint here. OK, so that also we are taking that into account. OK, another the thing is, if I have a constraint problem, then I can transform this into dual. OK, so G let us say new, and then I have to do a maximize of some function, right? And then I may apply the gradient descent here, and then I will need a gradient of g new and so on. So that's like one way to do. But another way is like I may use a Newton method, which looks like this. OK, so in a Newton method, I will use a second order information, and then I will try to form the KKT and so on. OK, so there are like two possible ways to solve this. OK, and here I have assumed that this was an assumption that we had made. OK, so if you are going via this route, then you must assume, because this is an iterative method, right? So you will have first delta x nxt, and then you will have second delta nxt and so on. So you have to make sure that delta nxt, the direction that you are choosing is a feasible direction. OK, so that is it satisfies this. If it doesn't satisfy this, you will be led to wrong answer. OK, because the equality condition is not guaranteed to be. If this happened to be something else, then x plus delta x nt, you have to maintain that all the new iterates you are producing is all equal to b, because they need to satisfy the equality constraint, and that is happening only when a times delta nxt must be 0. OK, so if you don't do that, then you are going away from the equality constraint, and hence your answer will be wrong. OK, because you are not satisfying the equality constraint, because the whole thing is not in the feasible set. OK, so one might ask, like, this seems to be like a strong condition, right? So it's like I have to check each time, right? So if I'm starting with an initial guess, OK, I mean, it may not be that tough, right? Because a is given to me. So essentially what I have to find is a non-zero vector, because if I choose a zero vector, then I did not move at all, right? I did not get a new vector. So the idea here is that choose a non-zero vector, OK, such that that is in the null space of A, right? So delta x and t is 0. So choose a non-zero, because 0, again, like you didn't move, right? Your goal is to update x to x plus v. So you need that. OK, you need that such that so it's like solving this equation, right? So you can use some maybe linear algebra library to find some good x as a starting point. Once you have found that, then the algorithm will take over, right? So then the algorithm will now find this this del x and t, and this del x and t will get updated, OK, by in the gradient step. So once you, because this is just a step, right? And then the new x will be given by x plus del x and t. And then once you get the new x, you solve another KKT system, OK, by computing the gradient effects at the new x, OK, and the Hessian also at the new x, and then you solve it. Then you get another x, del x and t, and then you update again, and then you keep doing this, right? So that's a iterative algorithm, right? So you have to keep repeating this. So what I told you is that there is this additional thing that you have to take care, that remember that if A is a full rank, that was the case that we discussed previously, right? If A is a full rank, there is no hope for you to find, because if A is full rank, the only solution for the Ax equals to 0 is 0 only, right? Because if A is full rank, then I can invert it. OK, so this non-zero del x nt is only possible for you when A is rank deficient, and that was the assumption that was made in this example, right? So A is like p less than n. OK, so A looks something like this, right? So that's like this. So in this case is like it's possible for me to find non-zero null space. OK. OK. So that's for this problem. If it is full rank, then we have already seen a previous example where we can write the KKT conditions again. So there it's fine. OK, but this is the specific case where you have A, which is a rectangular. OK, so there could the question is like, can we can we modify the Newton also for a infeasible point? Okay, so what I have done is for feasible, can I do it for infeasible? Like, can I have the liberty to start with any x, and the algorithm will take care of that, right? So let x denote the current point and assume that x is not feasible. Okay, but let us assume at least that it belongs to the domain of f. At least that is needed because we will compute gradients and so on. So that x should be there in the domain, right? So our goal is to find a step delta x so that x plus delta x satisfies x plus delta x goes to some optimal value, right? So the x star is the optimal value. To do this, we substitute x plus delta x for x star and w for mu star in the optimality conditions. Okay, so we substitute that x star and nu star in the optimality conditions and use the first order approximation of fx. So first order approximation of fx is this to obtain a plus delta x equals to b and grad fx plus grad square fxx plus A transpose. Okay. Okay, so we have used the first order approximation of f, and we have used the equality constraints, and this is the KKT for that. Okay, assuming that the second order approximation. So if I have that, then this will be there plus the equality constraint. Okay, and then I have ax plus delta x is equal to b. So that's like equality constraint that I must satisfy anyway. So whatever x I'm choosing, that must satisfy this. And this is the from the second order. I mean the first order approximation of grad fx will give me this. Okay, so it's like you change the problem to like this. Okay, so minimize grad fx plus grad square fx delta x. Okay, and that's it. And then subject to a x plus delta x is b. Okay, so this is the KKT for that. So if I do a KKT, this is the KKT for that. And this is a set of linear equations for delta x and w. So now if we can, yeah, so now we can put this in the linear system form. So grad square and so on. And this is what we get. So now the difference from the above is the second entry from the RHS. So this entry contains ax minus b. Okay, that's the residual vector for the equality constraint. So this is what we have put this in this form. Okay, so it's possible to extend a Newton step for the infeasible point via this. Okay, so we do an approximation of the grad, and then we maintain this. So that's like we are trying to enforce this. Okay. I mean, we have not said explicitly a delta x is equal to 0 right now. Okay, we have not said explicitly here, but this is incorporated here somehow. Okay, without even making any assumption here. And yeah, so and then this we have here, and we could rearrange this in this form. So yeah, so it's possible also to extend Newton step for the infeasible. So now you have the liberty to start with any x in the domain. Okay, and then you with this adjustment you can solve. Okay, so if we see the previous case, I think the change was only this guy. Okay, so to make this okay for infeasible, we have to adjust this 0 part here. Okay, so this this part here. Okay, so is ax minus b now. Okay, so it takes care of this, right? You can already see, right? So this is like a delta x. So last equation is a delta x is equal to minus ax plus b. Now I can take a common here. So ax plus delta x is equal to b, right? So this is taken, basically it's a small trick and that takes care of this. Okay, so that takes care of the equality constraints that must be satisfied. And yeah, so that will work for the infeasible case. Okay, of course there are approximations to the gradient that we are doing. Okay, so that may be a bit risky, that may not be a very good approximation, but anyway, these are approximation algorithms, right? So we are assuming that this is a good enough approximation of the gradient. Okay, because we are taking a step now, delta x. Okay, and the only way to pull out delta x is by stopping at the first. Okay, by doing this approximation like this, linear approximation, so the delta x comes out. And then the linearity and all this allows us to write everything in a matrix vector form. Okay, so this is still an approximation. Okay, it may be bad approximation. Okay, but anyhow, like there is a way to attempt solving a equality constraint problem. Objective could be non-quadratic also, it doesn't matter. But equality constraint problem can be solved via second order methods. Okay, so this is one example of that. So I think I will stop now. Okay, so in this last class we have seen variety of other methods, in particular coordinate descent we have seen, and then Newton method we have seen. Newton method is actually useful also in the equality constraint problems. Okay, what is left out in this course is inequality constraint problem I have not tackled. Okay, for that there are solvers like trust region method and so on. Okay, so those part has been left out. Okay, and somehow I was slow this time. Okay, these things were covered last time, but sometimes yeah, this time I could not cover the inequality constraint. So what we know is, like, I think we have covered the last 3 chapters are not covered from the Boyd book. Okay, so the last chapter was inequality constraint problem. Okay, and then there were like interior point methods and so on. Okay, okay, anyway, so I think we will stop here. And yeah, so I believe today we have exam at 5:30. So please be there 10 minutes before the exam. All will be elective. I mean all will be multiple choice questions, and it will be a sequential. Okay, so once you attempt, you cannot go back and re-attempt or even re-answer even answer an unanswered question. Okay, so that's so those are the things you have to keep in mind. Okay, I think with this I will stop here. So that will be the last lecture, and yeah, best wishes for the exams. Okay. Okay, bye.